Good evening, everyone. We will start our lecture in next 1 or 2 minutes. I'm waiting for few more students to join, and then we will start. Okay, let's start today's session. Good evening. I'm Rahul Chaudhary. I'm PMRF scholar for the course, and I'm an NPTEL TA for the course Analysis and Design Principles of Microwave Antennas. This is our fourth live problem session. So let's start with today's session with question number 1. So in question number 1, a 3-element array of isotropic sources has the phase and magnitude relationship shown here in this figure. Here we have given 3 antennas. One array is there which has 3 antennas arranged in this fashion along the z-axis, and the spacing between these element antennas are it's lambda by 2. So in this problem we have to find two things. We have to first find the array factor and then find all the nulls. I hope the question is clear. I will reread the question again. 3-element array of isotropic sources. So these elements means the antennas are isotropic sources, has a phase and magnitude relationship shown in the figure, and the spacing between the elements is lambda by 2. So we will start with finding the array factor. I hope the question is clear. Those who have joined just now, we have just started with question number 1. I will reread the question. A 3-element array of isotropic sources has the phase and magnitude relationships shown in this figure, and the spacing between the element is lambda by 2. We have to find the array factor and the nulls. So here this antenna 1, 2 and 3, they are placed along the z-axis, where the amplitude or the sources on the z-axis whose excitation are complex is given as for antenna 1 it is minus j, for antenna 2 minus 1, and antenna 3 plus 1. These are the excitation for the respective antennas. So I hope the question is clear. Now we will start with the solution for question number 1. I will draw the figure again. So the antennas are arranged along the z-axis. So this is antenna number 1, antenna number 2, and this is antenna number 3. And the excitation is for antenna 1, antenna 2 it is -1, antenna 1 it is -j, and antenna 3 it is +1. And their spacing between the individual element is d. So here 3 isotropic sources on the z-axis at z is equals to, first one, if I say z-axis, if we took this as 0, so antenna 2 is at plus d, antenna 1 is 0 when z is 0, and antenna 3 is minus d, or sorry, antenna 3 is plus, or whichever we think it is plus or minus. If we take this one as plus and this as negative, then antenna 3 is at minus d, and the spacing between them is spacing d, which is equals to lambda by 2. So kd will be equal to 2, k is 2 pi by lambda. So those who have just joined, I will repeat the question. We are solving question number 1. A 3-element array of isotropic sources has the phase and magnitude relationship shown in this figure. The spacing between the element is lambda by 2, and we have to find the array factor and the null. So these isotropic sources on the z-axis is at z is plus d, 0 and minus d, and the spacing between the element is lambda by 2. So kd is equals to, k is given as 2 pi by lambda, and d is given as lambda by 2. So it will be equal to pi. And the complex excitations are given, shown in the figure itself. They are, complex excitations are A2 is -1 for source 1, isotropic source 1, antenna 1 is -j, and A3 is +1. So in problem 1, first we have to find the array factor. This we have to find. Now for a linear array on the z-axis, for a linear array on z, the array factor is given by, is only the function of theta. It won't be varying with phi. Phi it will, because it's isotropic source, right? So that's why it just varies with theta. So f theta is given by, array factor is summation 1 to 3 a, and that excitation e to the power j k zn cos theta. So if I write down this, for antenna 2 it is a2 e to the power j k and Zn is for antenna 2 is d cos theta plus a1, because for a1 Zn is 0, and antenna 3 it is a3 to the power minus jk d cos theta. Now we substitute kd as pi, because k is 2 pi by lambda. Here I have shown you that kd is equals to pi, and an also we know, so f theta will become an for a2 is minus 1, so e to the power j d is 1 here, so it will become k is where k and d, if we replace k d is pi, and again cos theta, a1 is minus g, a3 is plus 1, e to the power minus j pi cos theta. Now we know that when e to the power minus j alpha minus e to the power j alpha, if something is in this form, we can write this in the sinusoidal form also, minus 2j sin alpha. So using this I am rewriting f theta as minus 2j. If you look in for these two, right, so we can write these two as minus 2j sin pi cos theta and minus j. So if we take minus j outside, I can rewrite this as 2 sin pi cos theta plus 1. F theta, and if I want to write the magnitude part of array factor, it is equal to 2 sin pi cos theta plus 1. So this is our required answer for part A of question number 1. I hope this is clear. And part B, we have to find all the nulls. All the nulls means where the array factor becomes 0. So all theta locations for which the array factor becomes 0 will be the solution for part B. So in part B we have to find the nulls, and they will occur when f theta becomes 0. That means 2 sin pi cos theta plus 1 becomes 0 at those theta positions or locations. When this whole thing becomes 0 will be the nulls. That means I can rewrite this as sin minus 1 or sin pi cos theta is equals to minus 1 by 2. Now what we will do, we will let this whole thing is x, let pi cos theta as x, so it will become sin x minus 1 by 2. Now if we write the general solution for this, for the x, where sin x becomes minus 1 by 2, we can write this as when x is equals to minus pi by 6 plus 2 pi n, or it can be minus 5 pi by 6 plus 2 pi n, where n can be any integer, means 0 1 2 3 4 5, anything, right? So, and we also know that this cos theta will be in between -1 to 1. So here this cos theta can be either -1/6 or, because what we assume that pi cos theta is equals to x. So now the cos theta can be -1/6 because cos theta lies between -1 to 1, in between this. So cos theta can be either -1/6 or it can be -5/6. So now for these values we can calculate theta, that is theta 1 can be cos inverse -1/6, and when we calculate this we will get 99.59 degrees. Next theta 2 can be, it will be cos inverse -5/6, which is equals to 146.4 degrees. So these are the two locations where the null occurs. So all the nulls for this given array orientation will be when theta is 99.59 degrees and theta 2 when it is equal to 146.4 degrees. So I hope this question is clear. If you have any doubt in this, please let me know. If it is clear, then we will move on to question number 2. Which of the following statement is incorrect? So in this problem, 4 options are given, 4 statements are given, and we have to select the incorrect ones. So the option A is, the primary purpose of using an antenna array is to increase the directivity of the radiation. This is correct. This statement is true only, right? That's why it's one of the main reason why we wanted to make an array instead of using a single antenna, because the directivity will be better. It will give a higher directivity compared to the single element of that array. So that's why we use it's one of the main reason behind using an array. And option B is, for the same number of elements, the beam width of uniform broadside array is broader than that of the uniform endfire array. Option C, folded dipole antennas has narrower bandwidth compared to simple dipole antenna. And option D, an endfire array antenna has maximum radiation in the direction of array axis. Option D is also correct, because that's what an endfire array does. It has a maximum radiation along the direction of the array axis. Now we have a doubt between option B and C. So now we are solving question number 2. Now for the same, if we look for the option number B again, for the same number of elements, the beam width of uniform broadside array is broader than that of uniform endfire array. So what this statement is saying, that if we have a same number of elements in broadside and endfire array, the broadside array should have higher beam width, but that is not true, because for the same number of elements, the beam width of uniform broadside array is narrower than that of end fire array. So broadside arrays provide a uniform. So what they do is, what a broadside arrays provide narrower beams with higher directivity in the direction normal to the array axis. Higher directivity in the direction of in the direction that is normal to the array axis. So what does it means? Now if we have let's say three antenna elements arranged in along the z axis, so the array axis is along the z axis, but it will have a array pattern something like this. But in case of end fire array, if we have three antennas along the z axis, it will have something like this. Now the directivity is along the maximum, or we say the major lobe will be along the z axis, means the array axis, in case of end fire array. And also it has a higher beam width, so its directivity will be less and the beam width will be higher. So the statement is not correct here, right? Because for the same number of elements, the beam width of uniform broadside array is narrower than that of end fire array. So option B is incorrect. Now we will look for option C. For folded dipole antenna has narrower bandwidth compared to simple dipole antenna. This is also not correct, because the whole purpose of using a folded dipole was to get a broader bandwidth. That's why they were used in radios and television transmission, right? Because they have a broader beam width so that they can support different channels. A folded dipole antenna actually has a wider bandwidth than a simple dipole antenna. So option C is also incorrect. So here correct options are, means the following statement, which of the following statement is incorrect or are incorrect, we can say. There are two options for this, option B and option C. These both are incorrect. I hope this is clear. If you have any doubt in this, please let me know. Otherwise, we will move on to question number 3. So in question number 3, a two element array of isotropic sources has the phase difference of phi and equal magnitudes. If the spacing between the element is lambda by 2, then determine the simplified expression for the array factor. Okay, so in this problem, two elements are given, two isotropic elements forming an array whose phase difference is pi and they have equal magnitude, and then the spacing between them is lambda by 2. So we have to find the array factor for them. So what is given in the problem is, phase difference is given alpha is pi, and spacing between elements d, which is lambda by 2. So now we have to find out the simplified array factor for it. So we know that the array factor is given by cos 1 by 2 beta naught d sin theta cos phi plus alpha by 2, where alpha is the phase difference. So in the problem it's given as 1 by 2, and beta naught is 2 pi by lambda, and d is given as lambda by 2 cos theta cos phi, and the phase difference is given as pi plus pi by 2. So when we solve it, we will get cos pi by 2 cos theta, sorry, this should be sin theta here, sin theta cos phi plus 1. So this is the required simplified array factor for the given array configuration. If we match it with the given options, we see option C is correct. I hope this question is clear. If you have any doubt, please let me know. If this is clear, we will move on to question number 4. In question number 4, a broadside linear array consisting of 6 dipole elements with inter-element spacing of lambda by 4 is given, which is being operated at 3 GHz. We have to determine the beam width of the main lobe. I hope the question is clear. A broadside linear array consisting of 6 dipole elements with inter-element spacing of lambda by 4 being operated at 3 GHz. We have to determine the beam width of the main lobe for this. Now we are solving question number 4. So the beam width of the broadside linear array is given by beam width is given by, so I think you guys have gone through the lecture videos, right? So I'm directly writing the formula here. It's given by, for a broadside linear array, is given by 2 lambda by n plus 1 into d, where this n plus 1 is the number of elements and d is the inter-antenna spacing, where n plus 1 is equals to 6 is the number of elements and d is the inter-antenna spacing. Hence I can now we just directly put the things in the formula. Bandwidth is given by 2 lambda divided by 6 into the inter-antenna spacing is given as lambda by 2 lambda by 4. In the problem it is given as lambda by 4. when you solve this, we will get 4 by 3 or 1.33, and if we convert it into degrees, it comes out to be 76.4 degrees. Now if we match it with the given option, option A is correct. I hope this is clear. Now we will move on to question number 5. So for question 5 and 6, the data is same, it's common here. So consider an ordinary end-fire uniform linear array such that the inter element spacing is lambda by 2 and the overall length of the array is much greater than the spacing. Given that the radiation pattern has only one maximum and the directivity is 20 dB above isotropic, so that means its directivity is 20 decibels. So in question number 5, we have to find the total number of elements in the array. So in this given configuration, the number of elements is not given. What is given here, the element spacing is given, and it's given that the directivity is 20 dB for this array configuration. So now based on the given information, we have to find out what is the total number of elements in this array. I hope the question is clear. So the given thing is directivity, which is 20 decibel. If I write it in linear scale, it is 100, and inter-element spacing is given as lambda by 2. Now directivity of an end-fire uniform linear array is given by, so I'm directly using the formula here. So the directivity for an end-fire linear array is given by 4n d by lambda, and it's equals to 100. And now in the problem we have to find the n, which is number of elements. So when we solve this, n comes out to be 100 lambda by 4d, and d is lambda by 2. Now when we solve this, it comes out to be 50. So the number of elements in the array is 50. So here the correct option is option C. I hope this question is clear. In question number 6, we have to find the overall length of the array is. For the same configuration, now we have to find the overall length of the array. It's given here that the length of the array is much greater than the spacing, which is just lambda by 2. So now we have to find the overall length. So again I will use the formula. The overall length of the end-fire array is given by L is capital L is n minus 1 into d. So n is 50 here, so 50 minus 1, and the inter-element display so the inter-element distance is lambda by 2. So when you solve this, 49 by 2 into lambda, which is 24.5 times lambda. So this is the length, overall length of the array. So if you match it with the given option, then option A is correct, 24.5 lambda. Now I hope this question 6 is clear. If you have any doubt in question 5 and 6, please let me know. Like if you have any doubt in the formula, you can refer to the lecture notes, because the derivation and all is given there. I'm not going to derive it again. Now we will move on to the next problem where the data is common for 7th and 8th. The antenna radiation pattern of a uniform linear array with total number of elements 2 is given by E theta. So this is the antenna radiation pattern for 2 element array. E theta is given by C1 into e to the power j beta naught r divided by r sin theta cos 1 by 2 b naught, so where C1 is a constant and spacing between the elements is d and the phase difference is alpha. So in this question number 7, if the desired direction of the main lobe is broadside, so if you want it to be the broadside, so I hope you understand. Let's suppose if it's oriented along the z-axis. This is my antenna 1, antenna 2. Now I want it to be broadside. That means the main lobe should be in a direction perpendicular to the array axis. So what should be the value of d and alpha? I hope the question is clear. So question 7, we know that broadside direction is given by when theta, for broadside theta is pi by 2 and phi is 0. Substituting these values, in the expression of array factor, we get cos 1 by 2 beta naught d plus alpha by 2. So what I have done here, this is the expression for the array factor, right? So I have substituted the values. If you want it to be in broadside direction, theta must be pi by 2. So this must be pi by 2 and phi should be 0. So that's what we got. And beta naught we know is 2 pi by lambda. So if you put it here, it comes out to be 2 pi by 2 lambda into d plus alpha by 2. So if d, let's say, so what we want is, we want it to be maximum, right? We want it to be 1, the array factor. In the case where theta is pi by 2 and phi is 0, means in this case, let's say it's along the z, so this should be like this. It can be any direction, just for reference I'm just telling. So in this case, this array factor should be maximum for 1. It will happen when only when d is some multiple of lambda, because we want it to be pi cos pi or cos 0, because cos can be maximum value can be 1, right? That's, and this alpha by 2 can be, alpha should be 0, alpha should be 0. Then we will get maxima along the broad uh, broadside direction, which is normal to the direction of array axis. Suppose this is our array axis, we want maxima along this direction. So this is possible when d is, the spacing between the elements is some multiple of lambda or wavelength, and the phase difference between them should be 0. So if you match it with the given option, so the correct option here is option A. I hope this is clear. And in question 8 we have to determine the phase difference alpha, so that the direction of the main lobe will be ordinary end fire. Means, let's say if it is these elements are like this, then it should be like this along the axis of array, along the array axis. The main lobe should be along the array axis. So for that case we have to find the alpha. Now I hope the question is clear. Now we are solving question number 8. So the main lobe will be directed towards the ordinary end fire direction for ordinary end fire direction for when alpha is either minus beta naught d for theta is equals to 0, or alpha comes out to be beta naught d for theta is equals to 180 degrees. So I have taken the same steps, whatever we have to check the array factor for this, right? So the solution will come when alpha is minus beta naught d for when theta either it is 0 degree or 180 degree. So that is, these two are the only possibilities in case if you want the array factor to be along the antenna array axis. So the theta can be either 0 or 180 degree. So when theta is 0, it should be alpha should be phase difference should be minus beta naught d, and when it is 180 degree the array factor the phase difference should be beta naught d. So the correct option here is option, both option A and B are correct, so option D is correct. I hope this question is clear. If you have any doubt in this, please let me know. So if this is clear, we will move on to question number 9. So we have to design a 3-element Yagi-Gouda antenna. So Yagi-Gouda antenna was earlier people used to for television, right? So they used to look something like this. So here we have to design a 3-element Yagi-Gouda. So it should look something like this, operating at a frequency of 185 megahertz, and the respective length of a driver. So it has 3 components, a Yagi-Gouda antenna: a driver, a reflector, and a director. So we have to find the length of these 3 elements. So I hope the question is clear. So now we are solving question number 9. It's given that the operating frequency of the our desired operating frequency is 185 megahertz. So we can calculate the lambda, which is C by F into 10 to the power 8 divided by 185 into 10 to the power 6. So the wavelength comes out to be 60 by 37, approximately equals to 1.62 meters. So again I am going to directly use the formula here for the 3 lengths. The length of driver element is given by LA is 0.45 times of lambda. So the length of the driver element is given by 0.45 lambda. So 0.45 times lambda is 60 by 37. So it comes out to be 27 by 37 approximately equals to 0.729 meters. And the length of reflector element is given by LR is equals to, for a reflector element the length is given by 0.55 lambda. So we'll substitute the value for lambda. So it comes out to be 0.891 meter, and the length of director element is given by is given by 0.4 times lambda. 0.4 and lambda is 60 by 37. So it comes out to be approximately equals to 0.648 meters. So if you match it with the given option is, then the correct option is A. 0. LA should be 0.729, LR should be 0.891, and LD should be 0.648. So the correct option here is option A. I hope this is clear. If you have any doubt in this, please let me know. If this is clear, we will move on to question number 10th. So for question 10th and 11th, the data is common. So consider a two element array consisting of folded dipoles. The center to center spacing is 6.13 into 10 to the power minus 3 lambda. So what it means here is, if we have a folded dipole, this is the length, and the spacing, this is spacing S, center to center spacing, and then this is the diameter D. So in the problem, L by D is given as 250, and the spacing S is given as 6.13 into 10 to the power minus 3 times of lambda. So in the question number 10, we have to find the approximate length of a single wire at its first resonance is. So in question 10th, approximate length of a single wire at its first resonance is. Four options are given. So let's move to the solution. I hope the question is clear. We have to find L. In question 10th, L by D is given, which is 250, and spacing is 6.13 into 10 to the power minus 3 times lambda. For first resonance, L should be 0.48 F times lambda. or I can write this as 0.48 lambda times L by D divided by 1 plus L by D. So I'm directly using the formula here. For the how we came to the formula, you can refer to the textbook. So see, L is should be equal to 0.48 lambda. So L by D is 250 and 1 plus L by D is 251. When we solve this, we will get 0.478 times lambda. So this should be the resonance for the first, this should be the length of the total wire for the first resonance. So the correct option, if you match it with the given option, is option B. And in question number 11, we have to find the diameter of the wire at the first resonance. That means we have to find D. For the first resonance, we already find out what L should be. So in question 11, L we know is 0.478 lambda, and L by D is 250. So if we substitute L here, because we have to find the diameter D, 250. So from this we can find D, which will be equal to 0.478 lambda divided by 50, sorry, 250. And when we solve this, we will get approximately D comes out to be 1.92 into 10 to the power minus 3 lambda. So if you match it with the given options, the correct option here is C. So I hope this is clear. If you have any doubt in the formulas, right, please for this question refer to the textbook, because there you will understand it in a better way, like how the formulas came. Or you can refer to the lecture notes also. I hope this is clear. If you have any doubt in the questions that we solved today, please let me know. Okay, if it is clear, then we will see some Rakesh had some problem in few questions, like one question number 10th and for last week. So I
Yes,
will
sir.
discuss that, yeah. So you had a doubt in where this IZ came, right?
Yes, sir.
So IZ is nothing like what I did in the next problem when I solved it, right? Instead of solving the loss like that, I directly calculated the whole loss. But here what I am doing here is, this I of Z is for a small element, and if you want to calculate throughout the length of the wire L, then that's what IZ is. IZ is nothing but IM. IM is the peak current which is flowing through the wire. So each section of the wire, I current is flowing through it, right? So what I am doing is I am
Right.
adding it, and the wire resistance we know for the per unit length. So I is already constant, so we will take it out, and R wire will be multiplied with L by 2. So that's why it looks confusing. That's why I gave the direct solution to you, because it makes more sense to solve it like this instead of the previous way with what I did. Because ultimately we want to find out what RL is. Because what we did it, why did we find it out P loss? Because our end goal is here to find out this R loss. From this P loss we find out what R loss is. But we can directly find what is RL is. RL will
Sir.
be whatever the length and per unit length resistance. RL multiplied with by total length, we will get 0.3125 ohms. So
So
that's
then
it.
integrating dz from 0 to L, how it becomes L by 2? So that was the doubt.
Oh, I think some mistake. This 2 should not be there, correct? Yeah, that some mistake is there in this solution. That's why I given you this solution because it makes more sense. I don't know why I did like that. Earlier I also got confused while solving it. So if you
Okay,
draw
sir.
the equivalent Thevenin equivalent, right, then it should look
Right.
something like this. But you understood this solution which I gave you, right?
Yes, sir. That is very good. Yes, sir.
That's how we should solve it actually. As unnecessarily I made it complicated by doing this. I hope this is clear.
Okay, sir.
Okay, then that's all for today. We will meet next Saturday, same time. Thank you for joining.
Thank you, sir.
Thank you.